I'd like to welcome Atman Dhruva to the stage. So Atman's our master's student. He's been working with us for the last 6 months. He's been working on a project to look at the operational use of UAVs for post-thinning assessments. And he's going to go through his research and a bit of a workflow on how you can derive some useful information from data. So without further ado, over to you. Anybody else ask the question as well? And the t-shirts are still up for grabs. So.
Welcome everybody. My name is Atman and I'm from the University of Otago, pursuing my workplace-based research project at Scion. I'm going to be talking about two things, giving a quick update about my project, and the second part will I'll be taking you through using deep learning tools in ArcGIS Pro. It's not going to be an exhaustive documentation. It's going to be like a quick walkthrough so everybody can start using deep learning. Right, so that's my topic. I'm assessing the optimal photogrammetry parameters for post-thinning quality control in radiata pine forest stands using unmanned aerial vehicles. Let you guys look at the slide just to take it in. This is the why behind my research. So to the best of our knowledge, there seems to be like a lack of thorough understanding in using parameters of image overlap. So that is forward and side overlap and ground sampling distance. This research also builds more upon the works of Julian Frey and Jacob Iglaut, who have in-depth assessed some of these parameters in forestry. So we decided that, since no work has been done in post-thinning, this would be like a novel introduction. The two UAVs from some of our fleet that we have, the DJI Phantom 4 Pro for RGB and the DJI M300 RTK with L1 for LiDAR. So this is like a table of some of my, well, all of my parameters. And I'm assessing, as I said, I'm assessing 9 different combinations of image overlap settings at 2 flight altitudes. So you have 2 ground sampling distances. This gives me 18 orthomosaics and keeps me busy and stressed for the rest of the year. Right, this was the study site. This was given to us by PanPack. If there is anybody from PanPack here, thank you so much. See anybody? Yeah. So this isn't a very good map. I apologize. We have the 30-day map challenge going on currently, but I really didn't have time to make like a proper map for the legend and the North Arrow and all that. But these are like the red dots are where we placed our GCPs, and you can check out our SOP for the importance of ground control points. Some people don't like to use GCPs, but I'm from the School of Surveying and I'm a sucker for precision and accuracy. So I'm never going to not use GCPs. This is about 30 hectares of post-thin radiata pine. It was, yeah. Right, so thanks to PanPack, we really did not know what kind of site they were giving us. And when we arrived on site, we were like, holy shit, that is like really challenging terrain and some really technical flying. Morgan asked me if we want to change the site, and I'm like, nah, bro, challenge accepted. If we can do it here, we can do it anywhere. So like just on, do we have a laser with this? Okay, no worries. So like up where you see the orange circle is where we set up our base, where we were like conducting our flight operations from. And we actually did like a little bit of a survey in person to figure out which spots would we get line of sight. But obviously, since it's a dense forest and mature trees, there's really nowhere where we could get line of sight. I want to throw this to you guys. When you don't have line of sight, what are you going to do? Anybody, somebody. Finish the job how? By flying without line of sight, but that's we'd be flaunting the rules then. Anyway, so we came up with an awesome solution for that. Yeah, no, it is a legal requirement. So we use like a 25-year-old mobile elevated work platform or a MUP. I'm pretty sure most of you guys have some cool MUPs at work. And we would encourage you to use MUPs when you cannot have sight of your drone. I'll give you one example. When we were trying to get this up and running, out of nowhere, like a bird, well, not a bird, a chopper flies at, like, comes out of the thin air, and he's flying like really freaking low near the canopies. And if we actually had two crafts in the air at the same time, and things could have gone horribly south. So like, yeah, it's good practice to use this. Yeah, we have David and Honey Jane on top of the view. It's exhausting, so like, thank you, epic job. Okay, so some of my methods and workflow, most of you guys are familiar with this. This is like really standard. On the left, we have a structure from motion, multi-view stereo workflow for my RGB imagery. And on the right is my processing in R and MATLAB for my LiDAR data. I'm not gonna bore you guys with this because I'm pretty sure all of you are already familiar with this. Okay, so what am I doing with my imagery? Now, to assess the quality of the photogrammetric reconstruction, I am assessing something called as ghost trees. And you can see what ghost tree means when the software or the algorithm that you're using does not pick up enough tie points around your object of interest. It's just going to completely omit the tree. And when you're taking inventory stock, that's not ideal. And the other metric that I'm using is assessing melted areas in orthomosaics. So melted areas usually result from a lack of overlap, which is a real problem as well. A third metric that I'm using is I'm going to be counting the number of trees in terms of stems per hectare. And I'm using a couple of algorithms. One is deep learning, one is an unsupervised machine learning algorithm, which one of our colleagues has been working on. It's pretty interesting and novel. And some of the anticipated outcomes from this project, it's going to further advance the knowledge of these parameters for forestry in New Zealand and worldwide. We're going to be releasing SOPs for to carry out post-thinning operations, as well as to use the deep learning tools in ArcGIS Pro. And hopefully a published article, which is going to be absolutely kick-ass based on the findings and insights of this project, because my methodology is going to be as interesting as my discussion. Not for real. Anyway, moving to the second part, deep learning using ArcGIS Pro. I see a big smile from Sarah back there. Yeah, so the slides and content have been inspired from various SB webinars, videos, ArcGIS Pro documentation, and other stuff on the internet. Again, as I said, this is going to be a quick walkthrough, so a lot of you guys can sort of. I just aim to demystify deep learning to most of you here. An SOP is going to be added to our website, and please always review and follow the documentation on the ArcGIS Pro website before you begin. That is going to be your best friend. That is going to be your Stack Overflow or your Stack Exchange. Anyway, right. Couple of points to keep in mind before you get started. If you are using the ArcGIS API for Python, which is super powerful, you need to clone your current environment. There are 3 ways of doing that. You can do that in the GUI, you can do that using the Python terminal, or you can go down the route of Anaconda. You also need some really cool hardware, GPUs. I would highly recommend you guys check out the website before going out and buying a random GPU to check for CUDA compatibility and drivers. Usually, like, the higher the memory, the higher the RAM on your GPU, the better the performance can be expected. And you can also, open your Windows command prompt and check out what exactly is your NVIDIA capable of, how much memory is it using, and it really gives you a deeper insight into what's happening behind your box. Okay, so a lot of you guys have probably heard of these buzzwords being floating around these days. And it's really easy to feel lost, overwhelmed, or like a bit confused. So I'm gonna like boil it down to like three main things or three overarching things. One is artificial intelligence, machine learning, and deep learning. Right. Again, image courtesy of Esri. Can somebody tell me what do you guys associate with artificial intelligence? What does artificial intelligence mean? Somebody. Yes? Awesome, that's right. T-shirt? Do you already have a T-shirt? No, okay. Right, so it refers to the ability of computers and like our machines to exhibit what we typically associate with humans. Can somebody tell me what do you mean by machine learning? Based on data-driven techniques, where you throw something at a computer and it predicts what you want it to predict. And deep learning is basically a type of machine learning, and it is like loosely based on the adaptiveness of the human brain and neurons and how information works in our brains. So in ArcGIS, we apply machine learning to perform spatial analysis. And machine learning has been around for a very long time. A lot of us have been using machine learning techniques without knowing that these are machine learning techniques. So I'm just going to broadly introduce you to some of the categories where machine learning is used in ArcGIS Pro. So the first is classification. Some examples of classification are your maximum likelihood, random trees, SVM, and it's very commonly used for land cover classification. Clustering, which is hotspot, multivariate, space-time pattern mining, Ansel local Moranza, which is like an index of spatial autocorrelation, based on Tobler's first rule of geography, where like things close to each other are similar than things that are further apart. The third one is prediction, and there's some awesome, that's one of my favorite forms of spatial analysis. You have your Bayesian greeting, ordinary least squares, geographically weighted logistic regression, wherein you're using geography to calibrate your factors and variables that have an influence on what you're trying to do. And one of our principal scientists, Mike Watt, he used a very interesting technique called the spatial ensemble method that sort of combines a couple of regression techniques. So why should we use deep learning for imagery tasks? Heaps of data coming available these days. You definitely need the right tools and the software and the hardware to manage big data. And deep learning is almost as good, if not better, than human eye. So much so that there used to be like a competition called the Visual ImageNet Challenge, where deep learning architectures were compared against like human error rates, and they had to discontinue the competition because these things grew really smart over the last few years. Right, some words associated with object detection in ArcGIS Pro. You have like, so ArcGIS Pro supports end-to-end workflows for deep learning, and you have something called this model type, which some examples are your SSD, single shot detector, Foster RCN, YOLO, it stands for you only look once. You have a model backbone, which is consisted of a set or a collection of convoluted layers, which essentially act as your image feature extractor. And annotations, labels, training data, potato, it all means the same. Right, just an example of how a faster RCN pipeline works, where you see the initial layers, you can think of it as a hive mind or like a really convoluted human brain. Okay, so the deep learning workflow in ArcGIS Pro, and I'm going to be talking about an object detection approach, can be broadly categorized or divided into 4 steps. So the first one, we label our objects, the objects of interest that we want the computer to pick up or detect. that is also like called creating training samples within the GUI. Second, we prepare our data and we export our training samples so that the model can be trained. We train our deep learning model and inference, where in this case, we're detecting objects of interest. Okay, so the first step, you open up your imagery tab on the green toolbox, go to classification tools, label objects. And you also have something called as a training samples manager. I have included this image on the bottom because I really want to talk to you about how important it is to create a good training data set and what you actually need to create a good training data set. The performance of your model is entirely going to depend on how you are labeled. So do not annotate like this. I'm going to show you how to do that. So first, you start out by drawing a polygon in various places on your orthomosaic, which have spatial variability. After you draw this polygon, you zoom in and you annotate every single object in it, and with perfect boundaries, with perfect borders, so that your model does not confuse an object of interest as background. And during the exporting step, like this main polygon, it goes into that little dialog parameter box, which says input mask polygons. So yeah, this is, as I said, just to reiterate, label thoroughly, label everything within the polygon. Do not leave out any part of the tree, even if it has some sort of ground or background, include that with your training data. So the ideal training data set and the best practice, generally speaking, if you have like the bigger the training data set, the better performance you can expect. Chips and tiles, I'm going to use this word and it means the same thing. Basically, when you are exporting your data, your image and your training objects are broken up into a user specified tile size or chip size. It's always going to be a multiple of 32, and 800 pixel is a good size to start. But then again, there's always going to be a trade-off between your tile or your chip size and your batch size that goes into the GPU to process at one time. Obviously, theoretically, it would be much easier if we had like one giant tensor and everything in it. But that's theoretical. Yeah, you need excellent annotations with awesome attention to detail. Use image augmentations. And when you're using the API for Python, using these functions, which are part of the ArcGIS.learn module called prepare data and get transforms, it applies transformations, various kinds. You can choose what kind of transformations do you want, right? And basically, like that gets you more bang for your buck because it's gonna like the computer is gonna learn from, let's say, one chip or one tile. It's going to augment, so like change the brightness, contrast, introduce Gaussian blurring, introduce noise, so that it learns even when, let's say, you have a blurry image, it still knows that this is what it's trying to detect. Just last week, I had the pleasure of meeting with Edward Wong from Eagle, and the way he explained annotation, like image augmentations, is like, if you teach a child to hold an apple, right, he's going to grow up saying, oh, this is a red apple, this is a red apple, this is a red apple. And then said person flies to New Zealand and sees a green apple and a yellow apple, but it's still an apple. How do you know it's still an apple? Because you trained your brain to recognize that this is still an apple. So as I said, like deep learning loosely on the adaptiveness, based on loosely adaptiveness of the human brain. So yeah, you label across multiple areas which have spatial variability, make a polygon extend around those areas, label extensively, and spend good enough time to create your labeling data set. The second step, we come to export training data. Now you see the geoprocessing box on the left. Input raster is where your fifth file goes, the map or the automosaic where you're trying to annotate and basically what you have open on your GUI. Additional input raster, you can leave that blank, create an empty folder in output. Your input feature class is essentially going to be the samples that you have exported from the previous step. Class value field you can leave empty if all of your objects belong to one class. Your image format, it's preferable you have this image format because that is what's supported these days. As I said, 800 is a good tile size to start with. And when you see stride X and stride Y, that is essentially overlap of your tiles. So like to create more training data, you will have like, let's say, a half to 25% of overlap between your chips. So you have like way more training samples. Reference system, map space, you can keep rotation angles 0 if you're just starting out with deep learning in the GUI. But again, if you dive down the ArcGIS API for Python, using those tools in the ArcGIS.learn module, you apply those augmentations and rotations for you. Metadata format is Pascal block or like visual object classes is nothing but like the format in which your labels are exported. So most commonly XML format in this case. When you do run this tool, right, we will have a folder, and when you enter that folder, there will be these files inside, right? You can go into your images folder and your labels folder, and you can check, just do like a visual QA/QC and see what your chips look like. And associated with each chip is you have a world file, which is nothing but 6 lines, including the X and Y coordinates, the depth, and the anchors of the bounding box. The third step, you train your deep learning model, and you can either do that natively in the GUI, or obviously you can go down the route of the API. Check out the developer's guide on the website. It is very powerful and very tweakable. If you have a custom model or a third-party model, or you have found something on GitHub that you want to like incorporate in ArcGIS Pro, using model extension in this library, you can easily do that and seamlessly integrate as well. Currently, ArcPro supports 1, 2, 3, 4, 6 object detection model types. Faster RCNN has been shown to be quite nice and quite accurate. So more parameters for the third step. So you input your training data, and when I say training data, that is the folder that you generated from step number 2. That entire folder needs to go in here, not images, not just labels, not just text files, that entire folder having those 5 or 6 different files. Your output model, again, create an empty folder. When you got the max epochs, let's say you're working with like a small to medium sized data set, you can use about like 20 or 25 epochs just to start with. And just to explain what an epoch is, it's just like it's one pass of a model, like a forward pass and a backward pass that constitutes one epoch. The model learns as it iterates over epoch after epoch after epoch. The model parameters, select faster RCNN to detect objects. As coming back to what I said earlier, it's going to be a trade-off between your chip size and your batch size. And you need to experiment a little to sort of understand what your GPU can actually take. So you can start with a batch size of 16, right? And if that does not work, ArcGIS Pro will immediately throw you an error saying GPU or CUDA out of memory. So start with 16. If you have like a NVIDIA 3090 Ti GPU with like 24 gig RAM, I'm guessing it is, you can probably use a batch size of 64. If you're just starting off with deep learning in the GUI, just change your chip size to 800, leave the rest as it is. The reason we do not populate the learning rate is because ArcPro does this really cool intuitive thing where it learns what is the optimum rate at which it can make a good model, essentially. So it all happens under the hood, so you don't need to worry about setting a learning rate for now if you're just starting. Backbone model, you can use less than 50, but like if you have a wider data set, like the more convoluted layers, the better performance you're going to get. It might take a little longer to run, but you can expect better performance. There is also an option of using a pre-trained model. And when I say a pre-trained model, it can be like a third-party model that has been integrated into Arc, or you can go down the Living Atlas and use a pre-trained model. Now, in terms of tree detection, currently on RGB imagery, there are 2 pre-trained models. One is a palm tree detection model, and the other one is an ordinary tree detection model. But when we're talking about plantation forests, these pre-trained models are not going to work because it's a whole other ballgame. You can have a validation. So like when we're talking about deep learning, like you have your training data, you have testing data, and you have validation data. So like, let's say you have 800 images. If you select 10% as validation, 80 of those images are going to be unseen by the model. So when your model is trained, it's then going to like see how well it performs on that validation data set. And all these metrics, you can actually view these metrics in model characteristics. There is a formula which I will take you through later. The two boxes that you see at the end, stop when model stops improving. That's a really cool feature that Esri has included. And freeze model. Now, you can take freeze model if you're running around 20 epochs, but if you have a really vast and like a varied data set, you should not take freeze model because it's going to learn better. It will take more time to process, but it's going to learn better if you have that option not ticked. Couple of available backbones for training the foster RCN model. You have ResNet 50, 101, and 152. Once you populate all of these boxes, you can also, so next to parameters, you have environments, and you can just change your process attack GPU. Don't forget to do that. And the result, the output from this step is going to be a .emd file. EMD stands for Esri model definition, and a .dlpk file. And the .dlpk it has all the information to do with running the inferencing tool in the next step. Again, please review and follow the documentation on the website before you start. So at last, we have inferencing, and in this case, we're detecting objects using deep learning. So as you see on the left, like the EMD file, that is the file that goes into the model definition box right there. Yes. No, because like I can't really see. Yeah, so input raster, already went through that, detected objects, and you have the model definition. As soon as you populate the box of model definition, the GUI, right, it will automatically like see what is inside the EMD file, and it will give you argument names. Right. Again, if you're just getting started with deep learning using OptPro, you don't really need to bother about this. Let the software do its thing and see how it's performing, because you can always go back, run it a second time, and then change some of these things. And if you want to know more about pattern threshold, I can probably talk to you guys about it after the workshop. Take the box that says non-maximum suppression, because what essentially happens is like when you after you run the inferencing, right? Let's say there's a tree here. Now, sometimes the model will have like overlapping bounding boxes on top of each object. Non-maximum suppression essentially merges those overlapping boxes into one. So you have like one box per object that you're trying to detect. Class value field is if you have one class, you can just leave it as it is. Confidence, just don't worry about it. Again, with this step, go into environments, change it with GPU from CPU. If you don't have a GPU, don't really bother trying to do deep learning. And also, you also would need to have the image analyst license. And I should have actually led with this. Go to the website, and that will like guide you through the GitHub page, where you can download the .msi and .cmd files. You'll need, these are installer files with all of the libraries that Esri uses for deep learning. So you need to install this, unzip it, extract all the files into your local folder, and then get started with this. Yeah, I can take some questions right now, but before I just want to say a big thank you to my supervisors, Robin Hartley and Todd Redpath at the University of Otago, the crew from PanPack, Sean and Morgan, and everybody at Sada who had me. It's also 16th of November, which is GIS Day. So happy GIS Day and good luck mapping our forests.